Hi everyone, we're finally getting to real coding today, so I'm excited about this. Talking about binary and stuff like that, all well and good, but I like getting my hands dirty. I like actually love coding itself rather than the theory and all this background that you need to know about computers before we actually get into it. Now, we could have gone over binary and hex and all that kind of stuff after we jumped into coding, but that little bit of wiggle room allows us to do the scratch programming, deal with numbers, and not have to actually code things, and then it's one of the many ways we could have approached this problem, or approached how to learn to code for the first time. But I like the high level theoretical underpinnings and then moving on from there. So we're going to be this is a multi-lecture apart, hopefully even more lectures than I would have normally done in other terms. So we're trying to break this down into small little chunks. We're going to go over the very basics, the fundamental concepts or constructs that C gives us, the various elements of it, like what are variables, that sort of thing. Then we're going to look at functions, and then we're going to look at process control and iterations and stuff like that. That's going to be a long time, a lot of different lectures. But first off, let's get to what we're going to be talking about. We're going to look at some of the very basic C elements, such as keywords and identifiers. We're going to do our hopefully either this video or immediately the next one. We're going to do our very first C program. It'll be very basic stuff, and there are some things you'll have to take on faith. We'll learn about C libraries and functions, and we'll learn how C works in general, rather than just memorizing certain things. Okay, so what have we learned so far? Well, we've learned that we can do programs are a series of operations. They're algorithms. They're very precise instructions for the computer to perform. And programming languages allow you to write in a more human readable format for exactly what you want the computer to do, step by step, as step by step instructions. And a program will run from the very first line of the program all the way to the end. That's all it does. There is no weird craziness beyond that. It goes from the start to the end, and that's it. Of course, as you might imagine, things do get a little bit crazier, but for the time being, starts at the top of the program, goes to the end of the program. That's all we have. An algorithm, when we talked about algorithms earlier, we talked about natural language describing, but non-ambiguous natural language to describe how things work. And we looked at pseudocode and we looked at flowcharts. And I would hope that you're going to still continue to use this when we actually start coding doing real code, because you want to think through the problem before you start typing, much like you do an outline to an essay or an outline to a novel before you start writing. It was a dark and stormy night. Uh, when we do pseudocode, it's a bit more formal than natural language, but there's still no ambiguity. But when you actually get to coding, it's not human, it's human readable, but it's not in English in any way, shape, or form. It is very precise, like math, essentially. And you have to do a particular way, otherwise errors will come about. We end up Programs are made up of two main parts. We have the code itself. This is the thing that's going to be operated on. These are the instructions that are given to the computer, and it depends on the language or the language you're using and the computer type. And then we have the data. The data is effectively just zeros and ones stored in the system somewhere. That's all anything is, and it is what your instructions can operate on. These could be variables, this could be a text file, this could be an image file, whatever it is. It's still all just zeros and ones. They're files, essentially. Uh, what have we learned so far? So what we're going to be doing, we're going to be doing a sequence of operations, a sequence of executions. Uh, if we can change the variable, if we have something that can change some number or something that we're storing around that can be changed, we're going to need something called a variable. This is something that we're able to set or change, like what is your name? Your name is a particular variable. Or how many students are in this class? That could be a variable, and might be able to change that over time. We looked briefly at loops in Scratch. There's definite and indefinite loops, essentially infinite loops and loops that only run a certain number of times. And what we will look at a lot more when we look at loops, We'll be looking at this in a lot more detail. But loops allow us to do the same operation over and over and over again until we want it to stop. We also looked at decision making, so how the program flows. It can change depending on conditions, like is that name equal to this? Is the number if this number of students in the class is greater than 47, do this. Otherwise, do that. And we looked at that when we looked at flowcharts. Um, Most languages have some way of modularizing code, bundling up common instructions, common things into one thing, into one set of instructions. So think of it as a subroutine or a sub algorithm. So if I want to find the minimum of a set of numbers, I might have that one part of my code, and I can keep on reusing that one set of instructions whenever I need to. That's what functions are all about. We'll be doing that very soon. And just to be very clear about this, I am not assuming anyone knows how to program before this. So it is difficult if you've been doing this for 20 years. It can be very difficult to know exactly what you pick up along the way in high school, junior high school, just reading the internet or whatever the case, or talking to your friends. It's difficult to know what you've picked up along the way versus what and is common knowledge for most people, or what is brand new information. So I'm expecting most people to never heard of two's complement, but you may have heard of binary before. You may have heard of bits and bytes beforehand, which we talked about last class. So if there's something that I'm treating as is obvious and it's not, please ask questions. Please stop. Please put a post in Piazza or whatever the case is, because I may have just overlooked something. It's very easy to do. By the end of the course, I'm assuming I can't. There's no assumption on where you come from, right? Like what high school you went to, that sort of thing. So when you get to 2400, I know what you've covered in 1400, and I know where the line is. But I don't know that line right now when I'm starting. So please ask questions if you have any. Okay. So if you want to know the nitty gritty, dirty history of C. Invented in 1972. Dennis Ritchie did it for Unix. Ritchie actually wrote one of the textbooks, or the recommended textbooks. And then later on, versions of it are ANSI C and ISO C. And C99 comes after that. That's the last time they upgraded or changed the language. Uh, and added new features. As far as I know, at least that's what from memory, at least, is in 1999. So C's been around for a very long while, and it's been fairly stable. But every once in a while, things change and they add new features or they add new characteristics. In case you're wondering, also, I have to double check this myself, but as far as I know, for what I was told, the story of when I was an undergrad, C is actually the third language. Yes, it's called C because there was an A and a B. Two other languages that didn't quite make it, didn't quite properly, when they're trying to make this new language, finally C is the one that actually ends up being used and properly developed. C++, on the other hand, is the running joke amongst programmers. If you have something and you just want to tack on 50% more, it is the bonus levels in Breath of the Wild, or the bonus content in Breath of the Wild, or whatever the case is. If you want what you originally had plus a little bit more, you put a plus plus in there. Um, and actually, Breath of the Wild actually has things like certain battle axes, like Lionel axes or Lionel clubs plus plus, which I'm assuming is a sort of a wink and a nudge to C++. It is a little bit better than what you had before. So in 1983, when object-oriented languages are coming out, they take C and they tack on classes. They sort of like bolt on a bunch of new features that you didn't have before onto C. Some people did not like C++ for that reason. It is inherently a language with another language bolted onto the side of it. So Java is built up from the ground up, but it looks like C. C Sharp is built from the ground up, looks like C. Python has a lot of stuff that looks like C. A lot of the ideas for C and C++ get applied in all sorts of other languages. JavaScript even uses these languages. The ideas, keywords, constructs, the approaches for C and C++, many of them are found in almost all programming languages, or most heavily used programming languages nowadays. I think Rust is also using C++ and C syntax. It is the precursor to so many other languages afterwards. And that's the reason we learn it, because not only is it still heavily in use today, so are other languages, but C and C++ are let you go really low level or really high level. So for both the IMD program and the net program, you can do both. You can just and use the one language. And on top of that, all languages you learn afterwards are going to look like C and C++. So you might as well learn the original. Okay, that's at least the philosophy. So things like Fortran, Algol 58, Algol 60 is what I think I learned at some point in time. Lisp is 1958. You're not going to learn any of those things, most likely. COBOL, you're not going to learn. Simula is not. You're not going to learn. And then C comes out. Now it says 69. 72 is actually the first, I think, official thing. Pascal comes out in 1970. Smalltalk comes out in 1969. There's been a bunch of these languages over time, but C ends up propagating to all of these languages afterwards. And if you actually got this image, you'll actually see like it just keeps on going. 1991 is Python, Visual Basics 91. It just keeps on going. There's like two other pages below this. But C is one of the things that influences everything afterwards. Algol you don't use anymore. Lisp is a functional language. You're probably never going to see that in your life. COBOL you may never see in your life. C is a language that you're going to see its influence on all of these other languages afterwards. More importantly, this is a bit old, 2012, but it's still fairly relevant. I looked at the numbers recently, and I think Perl is almost non-existent now. Python shot up a lot. Objective C is nowhere anywhere anymore. Java went down a lot. Rust went up, but pretty much Python is the big mover up in the charts, and maybe JavaScript. JavaScript and Python moved up in the charts, but the rest of this is been fairly stable. C is still heavily in use, and there's C++ in number four, the number four position. It's used far more than we want to admit because there's a lot of legacy code, but there's also new code. If you want it done right and done fast, you use C++. In fact, when you go, if the game design course that we have here is using, what is it using? Oh, darn it. I'm blanking on what language, but it's essentially C++ with an extra engine on top of it. There's a lot of things like the Unreal engines, C++. It's effectively C++. They just have already made libraries for you because C and C++ are fast as hell. All these other languages have a lot more overhead when it comes to running them, but C++ and C can be really low level. And so they're also, if you want something done really efficiently, C++ and C are the way to go. All right. So C is a compiled language. That's one of the reasons it's so blazingly fast. So meaning the program can execute. So if you take your code, your text file, that's all it is. It's a big text file. You pass it into the compiler. It squishes it down and makes it binary, machine code, but it's just zeros and ones that you can't read anymore. And that code can be run anytime, anywhere. So the source code is human readable. The machine code is run by the computer. They relate one to one another. And the machine code can be just executed anywhere, anytime, without any problems. That's part of the point as well. You don't have to run it in a browser or anything like that. It's code that just runs on the computer. That's when you find out that an executable will just be moved anywhere and just run. That's a pretty interesting feeling when you get that, because I was used to, when I was learning programming, I learned Java first, and then you have to use a Java interpreter and blah blah blah. You can't just run Java code. You can with C. So human readable, and we have effectively two different types of files that we're going to be dealing with. We have source files, which are .c or .cpp files. These are where your main program is. And then we have header files, which we're going to see later on. We're not dealing with header files a lot right now. They're additional necessary elements, but essentially you can think of them as a table of contents or a library. It is this stuff over here in this header file. We will hook everything up. It allows me to hook up different chunks of code together. And so it's like a table of contents for your code. Your actual code is in your CPP file, your C and CPP file. The header file is, by the way, these are the functions that you have available to you. The reason you want that is that I can pass my header file to anybody. They can look at the code say, oh, you have these 5 functions available. I can use that now. They don't actually have to see my actual original code at all. They can just use my code blindly use my code. And that's a huge, huge advantage. Now, it leads to other problems, but that is why we have header files in CPP. One of the reasons we have header files in CPP files. CPP files where most of your actual code is, and the header files are effectively what the functions that you are going to use are, where they're located, like the table of it, like a table of contents. For CPP files, for this term, most of the time we're going to have one file. That's it, and it's going to have a CPP as the extension. Why not .c? Well, because I'm lazy. Remember, efficiently lazy. So I had a TA last term say, "Oh my gosh, you need to rename your CPP file to be C because we're just doing C code." And I went, "Yeah." Right? Just because it has a .cpp at the end does not mean it's a C++ file. It could be just a C file that just has a .cpp. Visual Studio defaults to naming everything .cpp, whether it's C or C++. So the CPP stands for C++, in case you didn't realize that. You can call it .c, you can call it .cpp, I don't care. You just want to have a nice name. Um, you want the name of the file to be something meaningful, and you want to do good programming practices for how you name your file and what things inside your file are named. So my file could be a1davidspragg.cpp. A lot of your assignments are going to be like this. It's going to be the assignment number or assignment name, and then your name afterwards, so that if we get lost, or if something gets lost, or if you, heaven forbid, steal code from somebody else and you forget to rename that file and rename the name inside the file and a bunch of other things that you would have to do for making sure that you're cheating effectively, well, it's a lot more problematic for you. It's a lot easier to be caught cheating as well. But it also means if we grab something from CU Learn and we're looking at your code, we don't have to go back and find out who the hell's code is this. I don't remember whose code this is. Well, then your name's right on the file. I know exactly the assignment and the code, so that the TAs can grab a batch of all of your code and look at all of it. Your tutorials will have something like, here's your tutorial 2, and the name of the tutorial is called clock. That uses modular arithmetic, in case you're wondering. Um, and the only thing every single one of your programs, every one of your CPP files that you're going to be making this term have to have, if you have only one CPP file, you always need a main function. That's one of the, not quirks of C++, but it is, we need a starting position. It is the go position in Monopoly. It is the starting position, or wherever you go, and any board game or most board games have a starting position. That's your starting position. Then you go around the board, essentially, like if you're playing Monopoly. So we need a starting position. That's our main function. We always throw in a main function. That's where all your code is run. That's actually all your code for the entire program is in main, and then it calls other stuff. But main is one-stop shopping. That's, you have one and only one main method. Okay, we're going to get to this later on, but when we have more than one file, we have to worry about the order in which the files are read in. Your code is run top to bottom, one file after the other. That's it. So it's in order. It goes top to bottom. I would say, being compiled. And so if you don't put things in the right order, it doesn't know where the heck anything is. So if you have multiple files, you need to know the order in which those files are being put in. And if you're compiling your code, the code has to be in the order in which things are being executed. So if you have a function that you're calling in main, so you have something that main needs, it needs to come before the main method. The main function, there's one main function, and it can be put anywhere. It will find the main function. But everything else, it's based on order compared to the main function. If this is not really, so multiple files is not a problem for 1400. We'll do a little bit at the end of term, but for the time being, you have to worry about top down, the order in which your code is running in the one file that you have. So our program format for 1400, what we like to do, what we're going to be trying to do throughout the rest of term. I'm really bad for this, so I will just fully admit that I'm going to fall on my sword on this one right away. I have a tendency of getting lazy, trying to cut corners and being bitten in the ass every single time. Here's our approach. We will include at the very beginning all the different external libraries we're going to need, all the other header files we're going to need. This is everything, all the other external stuff. We'll see that with these includes that we're going to see. Then we're going to have prototypes. These are the, by the way, I will get to it, these other functions that I will eventually define later. They are meant to be IOU. IOU, one function named min, find min. IOU, one function called print out all student grades. Right? The functions that you will define later. But by putting them up here before your main, main knows about them. So what you get is main refers to this and goes, where is that? Oh, it's defined down here, and it goes back down. And now I don't have to worry about the ordering because the prototypes just say the names of these functions, the names of this bits of code that I'm going to need, the names of these little algorithms I'm going to use, and then I'm define them later on. So I have a table of contents, a main method, which is the main chapter or the main thing in my book, and then all of this stuff is the other stuff where all the other stuff is defined. Okay, this is going to be a lot of detail when we hit the real world example or the live demo. You'll see it in action, or some of it in action. Again, people will do this on a regular basis, and they go, "What's wrong with my code?" And I just want to be very clear about this. You can have one main method, one, only one, not two, not sort of another one, not one in another file. You can have one. Your program can only have one. The ring of power only has one master, right? The ring of power, there's one ring to rule them all, right? You can only have one main method, and that's it. And everything starts and ends with that one main method, and that's all you need to worry about. Everything else, main method needs to be able to find those other functions, find those other things. But the main method is the be all and end all of your program. Okay, I'll do the test drive in a second because we're going to see this in a bit more. I'll do a live demo of this. But yeah, I won't do the full thing. This is another assignment. So I want to point out a couple other things. For Windows programming, you need to figure out what your CPU is, your target CPU. Every single C program knows what the CPU is, knows what the operating system is, knows what kind of, if it's a 64-bit or 32-bit system is, right? To make your code work correctly, it needs to know all of this information, the target platform. And so every time if I build a Mac version a Mac version of the same code, I need to compile it with a different compiler with different flags with different information than with a Windows machine versus a Linux machine. So it is operating system specific. Every single time you make your program, it's operating system specific, which is weird. It's also old school, right? Windows needs to restrict what the program is able, what kind of abilities it has. So it reads in libraries. It has things like, I'm going to be able to do input and output. I need a special library to do that. I'm going to have graphics. I'm going to have images being able to draw on the screen. I need special libraries for that. I need this. I need special libraries for that. I need the standard template libraries. I need special libraries for that. If we have print and this printf, scanf, that sort of thing, they're all external libraries as well. We'll see that in action when we do Hello World. So we have a couple different approaches to them. This is what we're going to be focusing on here. They're console applications. These are the old school, like dead simple or the simplest approaches we have, which is it pops up a window, it outputs text to a screen. That's it. There's nothing else. There's no graphics, there's no mouse inputs, there's no this, there's no that. It will run it will execute a bunch of stuff, and when it asks for user input, you type in some stuff, and then it does a bit more stuff. It is what old programming used to be. It's a lot easier to do than other stuff that we're going to be doing, or other like things like graphic libraries and the like. So there's no graphics, there's no timing of events or anything like that. It's just sequential order. It's as simple as we can make it. Um, and normally the output is sort of OS independent. It all sort of looks the same, acts the same. If you're using a Mac for graphics, the instructions, the things you can do on a Mac are radically different than they are for Windows. And so therefore you would need a completely different set of instructions for for different operating systems. And so for other things like a Windows application or windowing application, like a graphic user interface thing, it will be completely different from a Mac versus a Windows PC. So here's a GUI application. This is a Windows Paint program, for example. It's very specific to the operating system, special operating system features, and you got to jump through a whole lot more hoops to get there. That's why we're not doing them right now. So we're going to get started with C++, with Visual C++. Now, it's a C++ compiler. The old instructions used to be do Windows 32. I think for most of you now it's like Windows 64. Most of your systems are Windows 64. 64-bit systems. That's what your computers are right now. But just in case you have a 32-bit system, I wanted to show that there are two different options, either 64-bit or 32-bit. Most of you just choose 64 if you have a chance. So Visual C++ for Windows 64. It's free for Carleton students. I've already passed a link off. I'm hoping you, in the first lecture, grab the link, have a look at it. And solutions are normally related to a project. So we have solutions, projects, files, like header files and CPP files, resource files. They are the bookkeeping. It's sort of like having solutions are like having folders. They are a way of organizing your code so they all sort of all the stuff plays together. The solutions themselves are not the important files. They're not your actual code. They're just where things are, right? So the my source files, my CPP, my C files are what you would submit for your assignments. Nothing else. You do not need to submit template files, resource files, DLLs, EXEs, anything like that. You submit your CPP or your C files. That is actually with the code that you wrote. The solution files and all this other stuff is just bookkeeping stuff, so that the when you're trying to compile your program, it knows where everything is. It knows where the other header files it is. It knows where that text file you're reading in is. So your CPP and your C files are the only things you really need to submit. The other problem is these source files, these projects, can be huge. There's a lot of extra cruft in these things. So just letting you know. When you compile a project, you will make an executable for the vast majority of time. Everything in 1400 and 2400 are going to be EXEs. Dynamic linking libraries are a different thing that we might get to later on in your degree program, but we're not doing them right now. They are libraries. You would be making a library for someone else to use, essentially. And any AXE that you make, when you've compiled and it works correctly, you will have a file with the extension .exe, and that you can just run. You can go into your Windows Explorer, look around, or go to wherever your file is, double click on the file .exe, and your program will just run. That's it. It's not special. It doesn't have to be in the IDE or anything like that. It is the program that you have made. You can run it anywhere at any time. Okay, so we're going to go over this rather than just go step by step through reading these instructions. I'm just going to make a Visual C++, a brand new project, and hope for the best. Live coding is always a little bit scary, but since this is not actually live, if you notice a little hiccup in the video, you'll know that I screwed up and I had to restart that particular video. Let's get to Visual Studio and see what we get. Okay, so let's keep this, and then after that point in time, then so this is what approximately we're going to look at, but we're going to get to actual C code in a second. So here is Visual C++. I'm using the code version of it, I do believe. I'm going to make a brand new project. Now, let me be very clear about this one. I like doing empty projects. I used to do console app all the time. I used to just always do this thing, right? I now only do this thing. Why? Because this gives me a whole lot of extra crap associated with it. It adds extra stuff to the project. And that would be all well and good for a basic project, but it means that that extra stuff means I can't share files with you as easily, and you can't share files with me as easily. They're auto generating certain variables and certain things with this, and therefore I can't look at it myself. It's harder to share stuff. So I'm doing empty project. Okay, and I need it to be make sure it's a C++ project. All platforms, great. I can do it for different operating systems as well. Project types, I can do a cloud thing, but I'm just doing all project types, C++ projects. There we go, empty project. Go to next, and then I'm going to choose. I'm just going to leave it there, but I'm going to move it over afterwards, just in case, because I don't know if I've set up that my directory structure. I'm going to make sure that all the code we write live is shared on a Google Drive that you guys have access to. You will have a direct link to that Google Drive. You can grab any project that we do in any of these videos and just grab it and look at it. There's no need for you to frantically write stuff down or try and write it down from the video. If you want to follow along code along with me, that's great. But and that's actually really good practice to make sure you code things out yourself. But don't worry about not being able to see the project again later. You will have access to all of these projects afterwards. So this is, let's see, lecture. Let's see, what are we? Lecture 4. Lecture 4. Hello world demo. All right, that's going to be the name of the project. We're going to create this. I just wanted something so I know that's a Hello World demo, and it's for Lecture 4. You'll see a whole bunch of crap, and I find this very intimidating at first. This is the only one we really need, right? Header files we're going to get later, the resource files later, but they're essentially blank right now. The source files, we're going to add a brand new item. So add new item, and we're going to make a CPP file, and we're going to call it HW main for Hello World main. Is there anything here? It's just Visual Studio. That's fine. All right, let's add it. That's it. Here's my CPP file. I'm looking at it right now. I'm going to need to include, so what do we need? We needed headers, prototypes, main, and I should be able to, I can't type today. Function definitions. Okay, this is what I said we were going to need. By the way, if you hadn't noticed, this means everything afterwards is a comment, as in the compiler doesn't see it, nobody sees it, it is for humans to read, and only humans read it. When you go to compile it, that gets just ripped out. You don't even see it anymore. It's not in the code at all. It is just for people to make comments to each other so you can see little instructions. It's like an annotation or a little a caption for a photo, right? The photo doesn't change. You just added a caption, right? This is what we're going to be doing. Okay, so we're going to include and IO stream, let's say. I could do an autocomplete there. All right, here's my main method. Int main. This is a singular function, one function that we're going to have do all the work. Okay, so we will get to functions soon enough, but this is what my main function looks like, and then I'm going to print f hello world, and we'll look at this in a second as well. All right, put a semicolon behind it. So here is a line of code that's going to be executed. I'm going to start my main method, do this line of code. Let's put another line in there. Copy and paste because I'm lazy. There you go. I'm going to make another line there. That's all it's going to do. It's going to run this line of code, then this line of code, then it's going to stop. We'll work on this. There are no prototypes. None for now. Right? There's no prototypes needed there, and therefore there's no function definitions afterwards. This thing, so now I'm going to compile my code. So I can go to build, and I can build the solution. Notice Control-Shift-B is a hotkey if I want to just use a hotkey. It's a faster way of doing it. So Control-Shift-B will build my solution. It will compile everything. Hopefully it's going to work. You'll look down here and okay, 1 succeeded, 0 failed, 0 up to date, 0 skipped. Okay, that means everything got executed. And look, we have a new file right in my directory structure right here, L4 hello world demo.exe. I could just double click that file if I find it in my home directory and look at hello world.exe. I can also do it right here. So I can just local window debugger, I can just run the whole thing. I'm just going to press the play button. Boom. That's it. Now, some of you may, if your console accidentally automatically closes at the end, which I really hope it doesn't do anymore, then we need to figure out something else. There are ways of locking this window open so that it doesn't automatically close. You want to leave it open at all times afterwards and then manually close it so you can see what the output was. Hello world, how are you? Great. That's all this thing does. Does this line, then it does this line. Notice if I get rid of this space, it doesn't matter. It doesn't matter at all. The end of the line is indicated by that thing right there. The end of the line indicated by that thing there. Doesn't matter how many spaces you put in between or how many lines you put in between. Doesn't matter. The semicolon tells you the end of the line. The start of my main method's here. The end of my main method's here. They're like jaws chomping down on the code, right? Where is the code in main? It's everything in between these two parentheses. Okay, that's it. That's your Hello World program. Once you get that going, then modify it. What you don't want to do is write everything and then see if it compiles. Because let's break something. Okay, I'm going to build it again. Control Shift B if I wanted to do that. And boom, badness happened, right? How do I know what the badness is? Well, it's expected. This is at least being generous this time. It's saying it's expecting something here, but it's saying it's on this line. Why? Because the end of the line had to be up here. So I look around the general area and go, where could that where am I missing? You're expecting a semicolon. Where could that be? Oh, I'm missing it right here. And then everything else goes away afterwards. This is how you end up trying to make sure your code compiles. You take a little bit at a time, write a little bit more, write a little bit more, and compile each time to make sure it's compiling correctly. You don't want to write 4,000 lines of code and then try and debug it afterwards. It's painful. Let me just state that for the record because I've done it numerous times. Okay, so that is your first Hello World program. I'm going to make sure you have this available and all other code that we write in this class available to you. But next time around, we're going to be looking at variables. And so we're going to get to what all of this stuff means and how all of it's connected together. Okay, this is just the first start. So if there's anything confusing, you can ask, but we're going to make sure we tease apart each of these individual parts. Like, what is a function and what the heck does this printf mean? There you go. So with that, I'll talk to you soon.